what we are looking at is a build up from what we've been looking at for the good past week or so. So, okay, let's just start from. Let me just check the notes. I went quite far when I was going through this. So, we discussed what normality is. So, for this question where you've been asked to find normality, how do you go about it? So, we discussed how you can convert uh, molarity, because you see that that's molarity, and then you can convert it to normality. We looked at that equation where you want to use the equation that we discussed last time. So you can go through this lovely exercise. It's really, really pretty much straightforward. So just use the equations. Uh, so like for this particular question, you can convert molarity to Yes. Is everyone able to see my screen? Hello, is everyone able to see my screen? Hello, if you can see my screen, let me know. Wait, you can't see it. Okay, really? Mm, you you can see it, right? Yeah, like you can see the notes, right? Okay, so I think you can just try to log out. Like for those that are not able to see, you can just log out, then log in. Okay, so you can convert molarity to normality, and you can now see. Okay, so you can convert molarity to normality. And how you do this is normality is equals to the number of reacting units times the what? Times the molarity. So that's a very important equation that you use in those questions there. So these are very, so you see there, we said to convert, you multiply the molarity times the what this times the number of reacting units, of which there you can see that's phosphoric acid. And you would know that in an acid base reaction, the protons are going to be the reacting units. And if they are the reacting units, meaning that phosphoric acid has got how many reacting units? Phosphoric acid has got three reacting units. So that's something that's very, very important to take note of. So they are not really, really hard questions, but in case you have any challenge in trying to answer them, please let me know in the group. So we can proceed to talk about statistics. Is everyone able to see the screen? Okay. So when we talk about statistics, yes, yeah. You try to check your syllabus. Try to check your syllabus. Really? Okay. Let's learn, and I'll send you. Yeah, but you were told that you had to study on it, isn't it? Hello. I think that's what someone said from your from yeah. Hello, is there anyone who can help us with this? Wasn't it that they told you that you had to study it, isn't it? Yes, but it is in your syllabus, isn't it? People is Yes, yeah, this question, oh sorry, this topic is in your syllabus. We were doing it in second year during our time, but because they've compressed the number of years for you, that's why you are doing it in first year. I checked your syllabus, it's there. It's there. It's actually unit 4. Unit 4.1 and unit 4.2 is the statistics component of it. Check your syllabus, it's there. Okay, so now we've discussed the methods in which you can do uh, your analysis and everything. But then statistics are very, very important because we know that the data which somebody is going to collect is going to have certain uncertainties in them. But we have to be sure of a certain degree of certainty. But we need probabilities, isn't it? We need statistics to be able to even design the correct experiment. Okay, and we'll look at that in much detail. So, what should the analyst know? First of all, like we said last time, you need to know the required size of the sample and then select the number of samples. So, like we said, that sometimes you may need replicate samples, right? Like whereby you get the large sample, then you break it into smaller samples, and then after you've broken them into smaller samples, what then you do is you say, okay, so maybe I'm going to have six replicate samples, which I'm going to use to determine how accurate, or rather, no, not accurate per se, but how precise my measurements are, how agreeing, or rather, in what degree of agreement are my values having. Okay, so that's important. And then also, once you've understood that, then you also be able to say, okay, which of these values which I've gotten are very accurate, and what could be the reasons for these differences in what, in accuracy. So you would want to understand all those things. Okay, so that's very, very important. Then the other thing, that the analyst must also express uncertainty in measured values. So you want to, so you don't just tell people to say, I think my values are not, I'm not certain. No, no, no. They have to know to which degree are you uncertain, so that even when they are using your values, they keep it at the back of their mind to say, these values that we are using, their certainty levels is what, is this. Imagine someone told you to say the certainty of getting COVID when you're not putting on a mask is 0.01. Then you don't care much whether to put on a mask or not. But if they tell you to say the probability of getting COVID without a mask is 90.7%, you're like, oh my goodness, the certainty is too much. So you'll be more careful, and you'd be more intentional about what, about putting on a mask, because you've seen that the probability of you getting the COVID is what, is very, very high. So that's something that's very, very important to take note of. Then you should also put the significant figures as well. But this is something that we discussed when we are looking at the measurements during the first part, during the first topic. So we really, really explained this in detail. But if you want to understand it better, you can use Zoomda. But we discussed it in good detail when that was the first topic we did in chemistry, and we also looked at difference between accuracy and precision. So you can go through this, but something that may be pretty new, maybe it's this, the errors. So there are two types of errors. They are the determinate or systematic, and indeterminate and random errors. So let's start with the determinant. So with the determinant errors, these are faults in a procedure. So the way you can look at it is, let's say maybe you are doing a titration, and maybe the one that you are doing the titration with is using a wrong instrument. What that simply means is, no matter how good or how well you are with regards to doing your experiment well, your accuracy is going to be poor, but you can find that your precision is going to be good. Now, why is this going to happen? It's because the problem is with the procedure or the instrument that you are using. So you are not going to be close to the true value, but the values that you are going to get are going to be close to one another if you are doing the experiment correctly, because the procedure is wrong, so you are far away from the true value. But because you are using the same procedure and the same instruments, and if you are and if you are very well, or very good in doing your procedure, you may actually realize that your values may even be close together, but then your accuracy may be poor. But the beauty about the systematic or determinate errors is that these can be found out. Let's say you are using a burette instead of a pipette. So then your demonstrator will come and say, no, you guys, you don't use a burette, you use a pipette. And once that is done, then you can actually be able to what? To correct the what? To actually be able to correct that error that may have been made owing to that fact. So that's about the oh my goodness. So that's about the determinate and the systematic errors. Then you've got then the other thing could be for this one is just giving examples about what those errors could be. So so what those errors could be could be maybe the calibration of the pH meter, or maybe your mass balance has got a problem. So that could be constant. So meaning throughout your experiment you'll be getting that same wrong value, huh? Or either the value can be higher or lesser, isn't it? And then there are certain variable. Let's say it's a temperature issue. You know, volume is affected by what? By temperature. And like we said, that's why molarity tends to be affected by what? By temperature. Since volume is affected by what? By temperature. That's why density of water, you've got a difference between the density of ice and the density of liquid water, isn't it? Because of that. Then sometimes these may be additive or multiplicative. Let's say you are getting that value, then you are multiplying it by, let's say, by a number, meaning that value is what? Is multiplicative. It's getting bigger and bigger, and that error is getting bigger and bigger. So that's really the thing there. So examples like we've talked about could be a problem with the mass balance, an improperly calibrated volumetric flask or pipette, so you keep reading the wrong volumes by the same degree. Then the other thing is the incorrect technique. Maybe you are supposed to do a back titration and you keep doing something else. No matter how good you are going to get the wrong values. So that's what determinate or systematic errors is all about. Then contaminated or impure or decomposed reagents. So again, that could be it. You are using expired things, so you find that you are getting that same error. It's because of a problem with your procedure, no matter how good you are. Okay, then the interferences, again, that falls under the impurities. So you can be able to identify these, because remember these ones are ones which can be found and dealt with. So you want to use standard methods with known accuracy and precision. So why should you struggle with trying to form a new way of forming of doing something when there are other ways which have actually been proven to work when you want to analyze something? Okay, so let me just save this lesson that we had so that I don't lose it. Okay, yeah. So yeah, so you always endeavor, or you always want to use methods which are standardized. That's why you use things like back titration. Let me check. Maybe there's some other ones to be allowed. So that's why you use things like back titration, forward titration, and all those things. And the reason you are doing all those things is because those are proven methods of analysis, isn't it? Then the other thing is that you run several analysis of a reference analyte whose concentration is known and accepted. So what you do is to also test your procedure is, like I said last time, where you go to where you know that okay, this sample contains 5 grams of copper. Then you try to find and calculate using your procedure to see how many grams you are going to find. If it's going to be very far away from 5 grams, then your procedure has got a problem. If it's close to 5, then you know that you're in good shape. So that's what this part is talking about. Then you say run standard operating procedures. So this is where you just have to be using standardized things. No need to create your own things when things that work are already there. Now, the indeterminate and random errors. So the sources cannot be identified, and that's the problem. Okay, so you can't identify them. and they can't be avoided, and neither can you correct them. Because, and this makes sense, if you can't identify something, then you can't correct it, isn't it? And if you, and if, okay, and if you can't, what's this, and if you can't identify something, there is no way you can actually what, you can correct that particular error. So that's something that's very, very important to take note of. And these are not constant. So you can find that maybe for this reading it's high, for that other reading it's low. But for the determinant and systematic errors, if your values are going to be higher than normal, they'll keep on being higher than normal. If they are lower than normal, it's going to be that. So that's really, really about it. Okay, so that's about it. So that's where the non-constant issue comes about. So the issue could be maybe in reading a mass balance. Maybe you are giving someone to read a mass balance. Someone can read it as 12.01, someone can read it as 12.02, someone can read it as something else. So these errors, in these random errors, because they can't be corrected, that means that, you know, all the measurements that we make, they are always going to have some degree of what, some degree of uncertainty. Okay, so you can't be sure to say, okay, I think what I measured is this, or what I didn't measure is that. There will always be a degree of what, a degree of uncertainty that's going to be hanging over your values. So that's an important point to take note of. So now, because scientists acknowledge that these errors are going to be there, that's where now statistics comes in to say what degree of what degree of errors is acceptable, because you don't just want errors anyhows, then that wouldn't really do justice, isn't it? So that's why it's very, very important to take note of these things. So that's that. Then random errors follow random distribution. So we are using the random distribution because these are random errors, and so they are going to be distributed randomly. You can't really say, okay, this is the error that I'm going to have. So that's why statistics deals with only random errors, because systematic errors, you can detect them and eliminate them, so there is no problem with them, isn't it? So now we now talk about the Gaussian distribution. So this is just something which is a symmetric bell-shaped curve. So that's just it, and this may look intimidating, but please don't let it intimidate you. I'll explain through it step by step, and you'll be able to understand the context. So results from a number of analysis from a single sample form follows the bell-shaped curve. So what this simply means is, if you are to do an experiment, and you've done an analysis from a particular sample, right? So let's say you, like that example I've been using for the copper ore. Let's say you get that copper ore, and then you do the analysis. What you're going to have is that your data is going to follow this particular curve. And don't worry, I'm going to show us the curve uh, in a moment. Okay, maybe let me show us the curve so that people can understand it. So that's the curve that we are looking at. Let me just reduce this so that people can have a better view of it. Let me just reduce this. Okay, yeah. So you see, so that's what we are having, right? So that's the Gaussian distribution. So you've seen where the mu is. Look at the center. That's the mu. That's the mean. And so that's what I'm sure you may have even. So that's what happens. So that's the mu. That's the mean. So what's going to happen is that if you are getting your data from a particular sample, what's going to happen is that there's going to be a certain value which almost all the values are going to be close to, and then they are going to be away, or they're going to be deviating away from it by a certain degree. So the where that thing you are seeing like a u, that's called a mu. Okay, and that signifies the what? That signifies the mean. Okay, the mean value. Okay, then the a, that's the height of the cave's peak. So in short, those are the values that you are getting. Let's say we are measuring the mass of, excuse me, let's say we are measuring the mass of the copper ore. So that a would be the mass of the copper ore, or that x or that y axis. Okay, that y axis would be the frequency of occurrence of a particular result. So let's say you are getting, so here you might have your values, isn't it? So your values may be there, and then that mean value is going to be there. So what's then going to be happening is that when you are distributing these values, you are going to be seeing that they are going to follow that particular shape. Now, there is a difference between the values which are obtained from a finite number of measurements and those obtained from infinite number of measurements, and we'll look at it. But for now, this is just the Gaussian distribution. So you see that there will be the mean value, and here on the y-axis, those are the different values that you'll be getting, and then you are going to have the mean, and then you are going to have all those values. So that's that. So then what is the sample mean? So what the sample mean simply means is that it's the arithmetic mean of a finite number of observations. So what also known as the average. So what this simply means is, if I get my copper ore and I've done my analysis, and for my analysis, what I've come to find is that, let's say I've used maybe six replicate samples. What's going to happen at that particular point is that when I get the different values which I've been getting for the copper ore, or for the amount of copper in that copper ore, I'm going to get those values which I've gotten. I'm going to add them, then divide them by 6. Since those values are 6, if those values were 7, I'll divide their sum by what? By 7. Or so you just get the sum of the measured values divided by the what? By the number of measurements. So that is the sample mean. So it's the arithmetic mean or average of a finite number of observations. Finite simply means it's something that you know the numbers, the number of samples that you have. That's what finite means there in that context. Then what you're going to get is the population mean. So this simply talks about the limit as n approaches infinity of a sample mean. So this simply means is that for the population mean, you see that's a mu. Why you are saying that this is going to be an infinity? It's because you are looking at the fact that, okay, so you are looking at the fact that this particular, when you are doing a census, not everyone gets to be counted. That's just the fact. Some people may be home, some people may be what, so not everyone is going to be counted, isn't it? So when you're doing the population census, it's an infinite number of sample, because you don't know exactly the people that what, that you've measured or that you've been looking at. So that's why the sample mean, it's for a finite number of observations. For a population mean, it's going to be for an infinite, okay? Because you're not really sure exactly what is happening. So that's an important point to take note of. Then you've got the so you see, the mu is equal to the t in the absence of systematic error. So what was the t? Maybe in case people have forgotten, the t is simply the accepted value. Okay, so meaning, if let's say you are sure that there is no systematic error, that you tried to do your sensors pretty well, then you can just assume to say, you know what, this population mean, even though we are just trying to approximate, but it's something that should be pretty accurate. Okay, so now in those values that you're going to get, there is always going to be an error. Okay, so there are a number of areas of errors that we are going to talk about. So remember, the error can either be, so error is the difference between t, which we know is the accepted value, and either uh, a single, so that xi, that's a single figure, isn't it? And then that x with a dash on it, that's the sample mean, isn't it? So it simply means that when you are calculating the error, you can either get the error for each individual value, or you can actually get the mean of those samples. Then you what? Then you subtract from the accepted value. So what is the accepted value? I'm sure you've heard of things the true value. And the best example that I would give is that experiment that you do in physics, where you are trying to find the value of g. Now you know what the value of g is, isn't it? It's 9.8. So that's your accepted value. That is your t. So in that experiment, people get different values. Some get 10, some get 8. So that you can either get the error, you just get that one value that you've gotten, and you subtract it from, or you subtract the true value from it. Or if you've done a number of measurements, you get the average of those measurements, then you subtract the accepted value. Then that's going to give you an idea of the error that your value has. Then the absolute error. So absolute error, we know what absolute is. Absolute is you don't want negatives, right? So it's just the same. The error, then you just get its value and you make it absolute. Meaning if you had a negative, you make it a positive, just like that. And of course, a positive error remains a positive, because the absolute value of the positive value is going to be the same positive value. So that's about it. So then the total error. So the total error is simply when you are adding all the systematic and random errors, so that people have an idea how much they can trust your data, isn't it? So that's an important thing. Then relative error. What is relative? Relative error, when you talk about relative, you are simply comparing something with something, right? It's almost like a ratio, isn't it? So that's the best way you can remember it without memorizing. Relative, it's almost always a ratio of something to something. And we know that division is by definition a what? A ratio. So relative error is you get the absolute error divided by the true value. So let's say if your the difference between your true value and between the value that you found and the true value. Let's have an example. So if let's say the value that you found was 2 grams and the true value is 1 gram, so when you subtract the two, you get your value, you make the absolute, it is going to be 1. So you are simply saying the value that you found, the absolute error that you found, 1 over the true value, which is what? Which is, okay, let's make it, the error you found was 1 and the true value was 3, isn't it? So that's going to be 1 over 3. So that 3, when you do that division, that gives you the relative error. So it's more or less like you are now getting a ratio of the error that you had in that particular question, or rather in that particular measurement that you were looking at. Then relative error percentage, of course, it's just relative error multiplied by 100%. Then you get a percentage relative error. Okay, then we now go to standard deviation. So what is standard deviation? So we start with the absolute deviation to begin with. So when standard deviation, what is deviation? Deviation is just how, by what margin s- a value has moved away from the mean. Okay, so let's say you've gotten your samples and your mean value is, let's say, 5 grams. Then let's say you've got a value which is maybe like 6 grams. So then you want to calculate what is the absolute deviation, by how much, by how many grams has this value moved away from what? From the mean value of 5 grams. Or let's say you are calculating distance, by by how many meters or by how many centimeters has this value that I've found deviated from the mean value. So you are simply subtracting that particular value minus the mean, and because it's absolute, meaning when you get a positive number, it remains a positive number. You get a negative number, you make it a positive number because it's absolute, absolute deviation. So that's about it. Then relative deviation. So remember, relative is, you are always dividing something. It's a ratio. So always think of it as a ratio, right? So relative deviation is the absolute deviation divided by the mean. So really, it's not something to memorize. You just remember relative deviation. Relative always means a ratio. So you are getting the absolute deviation and dividing it, rather dividing it by the mean. Then you get your relative deviation. If you want to get a percentage relative deviation, it's just multiply the relative deviation by 100%. Then you've gotten your value. Then we now look at standard deviation. So really, when you are looking at the sample standard deviation, you are simply pretty much looking at a measure of the width of the distribution. In short, how uh, how really are the values differing from the mean? Okay, so let's say you've got a mean value, and we'll look at the Gaussian distribution in a short while. But what you're basically looking at is, you are looking at the mean value and saying, for that mean value, really, how are things differing? How are things deviate? How are my other values being either above or below that mean value which I have? And so when certain measurements, or when a set of measurements has a small standard deviation, the distribution curve is going to be narrow. What do they mean when it's going to be narrow? It simply means that what you're going to get on this particular diagram, let me see if I can write here. Can I write in here? Anyway, but what this simply, okay, no, I can. So what simply means is, I know it's not possible for me to write in here. Okay, so but what this simply means is, if your values have got a small standard deviation, meaning that they are not deviating from the mean by a huge margin, and because they are not deviating from the mean by a huge margin, this means that uh, your values are not far from one another. And if the value, okay, what is this? Okay, okay, what did I do? Oh yeah, anyway, so what this then means, it simply means that those values which you've gotten, okay, are not very, very much different from what? From one another. And because they are not very much different from one another, it then entails that your distribution curve is not going to be wide. And don't worry, I'll explain that in a short while using a diagram. So that's the formula for the standard deviation. You are simply getting, so anyway, so it's basically the deviation, you call it the absolute deviation, over the number of degree, or the degrees of freedom. So degrees of freedom is simply number of observations minus one. So, or rather, number of, let's say you are measuring 9 things, then your degree of freedom is 9 minus 1, which is 8, isn't it? So that's what the n minus 1 is for there. Okay, then you see that deviation there squared is the same as uh, the difference between that particular measurement minus the mean squared. Now, when you square something, it doesn't matter whether it's positive or negative, it's going to be positive, isn't it? So that's why we don't tend to use the absolutes in here, because whether you use absolute or not, you are still going to get what? You are still going to get a positive. But of course, we see that the absolute deviation there is what we are using, but I just wanted to point that particular point out. So then there is also the standard deviation of the mean. So that one was the sample deviation, okay? So just know how to differentiate them. So the one here, remember mean, you've got what? Number of observations, but for this one you use degrees of freedom. So if your n is, if the number of things that you observed, let's say you maybe had maybe six replicate samples, so meaning you say 6 minus 1, okay, then your degree of freedom is what? It's going to be 5. Then standard deviation, so you're going to have standard deviation of the mean. So that's a standard deviation of the mean. That's so it's just basically the sample standard deviation over the square root of the measurements. So it's pretty much, you have to find the sample standard deviation using this formula. That's going to be the small s there on top. Then to find the standard deviation of the mean, you just get the standard deviation over the square root of the number of measurements. So let's say you found your sample standard deviation to be 0.1, and you were looking at maybe 7 samples. So you have to say that number, sample standard deviation over square root of 7. Then you found your standard deviation of the mean. So that's how they would ask. Let's say a sample or an investigation was found, the sample standard deviation was found to be this, and the number of samples looked at were 8. Find the standard deviation of the mean. This course is one of the okay, this course was one of the easiest at second year. Yeah, like for most people, you get a deep, you get a B plus. People would complain because this would be a course where people would do really really well. So it's not really, it's yeah, it's just about knowing, understanding the concept, and also understanding the and also knowing the formula. Yeah, the formulae. Okay, so now you've got now population standard deviation. So remember, whenever you're talking about a population, remember the example I gave about census. They don't count everyone in census. That's just the thing. Like you can't say that when they do the census, they count everyone. So whenever population standard deviation comes in, think of infinite number of what? Of measurements. So that's why you've got that limit. Where when we start doing calculus, I'll explain in more detail what limit means. But for now, just know that you're talking about infinite. You can't really tell how many measurements were looked at. So in that case, you look at the what? Population standard deviation. So for this one, you get the mu. You remember the mu that we found some time back. So you just get each value, subtract from the mu, you square it over n, and then you find the square root. Then you found your population. So the difference between this and the sample standard deviation is that for this population standard deviation, you don't find the degree of freedom, isn't it? Because you don't subtract the number of measurements by 1. So that's an important point to take note of. Then we now have percentage relative standard deviation. So like I said, every time when you see relative, then you are dividing something by something. So relative standard deviation is simply the sample standard deviation. So remember, the one that I'm saying, the sample standard deviation, is that one that we started with, the one where you get a value, subtract the mean, square over the n minus 1, or the number of measurements minus 1, which is the degrees of freedom. So you find that sample standard deviation over the mean. Okay, so the mean value of the samples that you are looking at, and then you found the relative standard deviation. Then to find percentage, you just multiply that relative standard deviation by what? By 100%. Then there is a concept called the variance. So variance, this is just a square of the standard deviation. And how they used to love bringing questions is they would give you the variance, and then in the question that you are supposed to solve, you have to use standard deviation. So people would get stuck. Okay, but they didn't give me standard deviation, but how do they want me to find it? You have to remember that the variance is simply a square of the standard deviation, both the sample standard deviation or the population standard deviation. Okay, so you just have to square it then. So you just have to square the variance to find your respective standard deviation. Okay, so it's a measure of precision. Okay, so and one thing to take note of is that the variance is additive, but standard deviation is not additive. So meaning for the variance, you can get the variance, and so if you've got an error, let's say in your variance, they are going to be additive, isn't it? But standard deviation is stands alone, isn't it? So it's not additive. Okay, so if you want to find the total variance, remember you said that it's what? It's additive. So you can find total variance. You just add the sum of independent variances. But standard deviation is not additive. So quantifying random error. So uh, we're going to look at terms such as the median. So median, this is just simply the middle number in a series of measurements arranged in increasing order. So like how they used to do it for our tutorial sheets, they will give us numbers or values, let's say masses, and then ask us to find the median. So you just have to arrange them in increasing order. You start with the small one to the largest one. So after you do that, if they are, let's say they are they are an odd number. Let's say they are three, they are five, they are nine. Finding the median is easy because there will always be that one value that stands alone. But when you've got your measurements which are even, let's say you've got let's say when you've got six measurements, you don't have a middle number there, right? So what you do is, if you've got an even number of measurements, you get the numbers which are which are in the middle. Let's say you've got the numbers 1, 2, 3, 4, 5, 6. What you do is you get the numbers which are at the middle. It's what is 3 and 4, isn't it? So you add 3 and 4, then divide them by 2. So you simply find the average of the two middle numbers if if the measurements are what? Are even. And so you can't really find, and you can't really get to find a what's this. You can't find a median, huh? So that's the point. Then what's the mode? The mode is just a value that occurs the most frequently. So for this one, like what they will do is they will give us the masses and then tell you which one has got the what has got the mode. And if they are all occurring one time, then the mode is not there. Hmm? Okay, then what's the range? The range is simply the difference between the highest and the lowest values. So whenever you're given this kind of question, it's good to always arrange them in increasing order because you easily find the median and you easily find the mode because you see those values which are close together. Then you know that, and then they are the same. Then you know that they are occurring more frequently, isn't it? So that's a key thing to take note of. Then the range, when you've arranged them in increasing order, it's easy because you just look at the first one and the last one. Then you subtract them. Okay, then you've gotten your range. Okay, great. Okay, we're only remaining with this topic is long. Anyway, they tried to compress the entire of analytical chemistry into uh just one unit. So that's why it seems a lot. Yeah, because we used to learn this course for 6 months, so you can imagine. But not just this, but other things as well. Anyway, so quantifying random error. So Gaussian distribution, which is that curve that we've talked about, and statistics are used to determine how close the average value of measurements is to the true value. So the Gaussian distribution assumes infinite number of measurements. So what they're basically saying here is, for the Gaussian distribution, you can't really say that no, here I'm looking at like you assume an infinite number of measurements. So that's why you can use this for maybe probably sensors. You could use this because whenever, like, let's say you are trying to find how many people have reached grade 7, so you find that there will be the mean, a lot of people have reached grade 7. Then there will be on either end those who stopped at grade 9, and on either end those who stopped maybe at grade 6. But the point is that there's going to be a mean number, okay, in that census that you'll be taking, depending on what your question is. So that's what they're saying. So now what they're basically saying is that when you are doing a census, because you've got an infinite number of measurements, we talked about the fact that we usually use mean for a finite for finite measurements, meaning for measurements that we know where they are starting from and where they are ending, right? Let's say I measured 10 things. So meaning your n is what? Is 10, right? Like your number of measurements. But then as the number of measurements which I'm having are increasing and they are approaching infinity, what happens is that the difference or the absolute difference between my mean and the mu, it's going to be what? It will be approaching zero, because remember, you are dividing this number, the difference or the absolute difference, by what? By n. So as n, or as the number of measurements increases, this value, we know that if you are dividing something and the denominator keeps on increasing, you keep approaching what? Zero. Like you saw for that question for the gravitational force that we were looking at in physics. As r was increasing, we were seeing that the values were actually approaching what? We're actually approaching infinity. So that's something that is important to take note of. So that's why for this question, or when you've got when n is greater than 20, so meaning when you've got more than 20 measurements, you can safely assume that your mean would be almost same to what? To mu, because the difference is going to be close to what? To zero. So that's what this part is explaining. Then for the random error, you are going to get the mean, you subtract the mu. So that's basically it there. So the standard deviation coincides with the point of inflection of the curve. The point of inflection, the two inflection points, since curve is symmetrical. So what this says is, you see there population mean, that's the mu down there, I'll show you, and the true value there. So what this simply means is, you see where your point of inflection, it's that point and that point. So you see that's where your standard deviations are. You see that symbol, that's for population standard deviation, and that. And I'm going to explain now what I was talking about. So then using the Gaussian distribution, you can then be able to find the probability of maybe how close your values are to the real thing, to the true value. So how this happens is, you use the you're going to use what we call the ranges, okay, and the Gaussian distribution. So what this means is the percentage of measurements lying within a given range. So that's probability, isn't it? So, and don't worry, I'll show you this on the diagram. So what you're having is, look at the first one. If you've got the population mean plus minus one standard deviation, then it's going to cater for 68.3% of the what? Of the samples. If you've got the population mean plus minus 2 standard deviation, you're getting 95.5. And if you've got population mu or population mean plus minus 3 standard deviation, 99.7%. So what this simply means is that the more the standard deviation or the more the deviation from the mean, the more values you are going to have. And let me explain using the diagram. Okay, so we know that of course we can say the average measurement is reported as mean plus minus standard deviation. We've explained that. It's important that the mean and standard deviation have the same number of decimal places, okay? So that there is no ambiguity, okay, in the values that you are being looked at. So these are things which I've looked at, that I've explained there, but the diagram is going to explain, yeah, exactly. So now, this one now it's what mu plus minus standard deviation 1. So you see that the values, okay, let me just reduce this so that people can see this better. So what this simply means is, you see here what you're having. It means that the values which you are getting from the mu, you go plus or minus. Minus you go to the left, plus to the right. So this is the what? These are the values, or this is the sample size which is falling within this range. And this is called the what? The confidence level. So meaning that if you say I'm looking for a value which is plus or minus the mu amongst the sample. So you've got a 68.3 confidence level to say you're going to find that particular value with a chance of 68.3%. Now, if you increase the random error, or rather when you increase the deviation, the more you increase the deviation, the more sample you are actually going to have. Okay, not necessarily that the sample is adding, but the more you try to find someone, or okay, let's say you are trying to find let's say the best to okay let's look at in terms of results for School of Natural Sciences. Let's say they are trying to look at people that got 90 to 100%. They are going to be few. But when you get from maybe those who got between 40 and 50, you find that there will be a lot. Okay, so that's just basically what this particular graph is trying to show, and that particular graph as well. So tomorrow we are only remaining with about 29 pages. So I'm sure tomorrow we should be able to wrap up this topic. I know it's been long, but it definitely seals up a lot of things. So I don't know if there are any questions before we can be able uh, uh, co- uh, to call it done. Are there any questions?